Welcome to the first video of Organic Chemistry course series. In order to begin learning this unbelievably extensive branch, we need to have a quick revision on some basic chemistry and somehow physics knowledge in the following videos. Let's jump to our session and waste no more time. Speaking of molecules, we all know that bonds keep the atoms near each other so that molecules can form and remain still. It's really important to know two essential rules here. Opposite charges attract each other, while like charges repel. When two atoms get close to each other, the positive charge located in the nucleus of the first atom attracts the electrons of the second atom and vice versa. So as a result, the bond forms between two atoms. This bonding is simply described by Coulomb's law, which says opposite charges attract each other with a force inversely proportional to the square of the distance between the centers of the charges. This attractive force causes energy release as two neutral atoms are brought together. In chemistry, this energy decrease is called bond strength. When two atoms are posed in a particular distance, energy stops releasing. This distance is called bond length. Well, what happens if you try to make them get even closer? The answer is a really sharp energy rise. When atoms are too close, the repulsion of like charges becomes stronger than attractive forces. On the other hand, while the atoms are at the distance of bond length, the energy content of the system becomes minimum, and the bond remains at its most stable situation. Another way that atoms can connect together is called ionic bonding. In this type, one or more electrons completely transfer from one atom to the other, so as a result, two charged ions will form. Cation, which is positively charged, and anion, which is negatively charged. The bonding can again simply be described by Coulombic attraction between two ions. In this picture, you can see a really simplified version of illustration that shows the difference between ionic and covalent bonding. When we take a look at carbon, in some compounds, some atoms bind to carbon in an intermediate between these two types. Some ionic bonds have covalent character, while some covalent bonds are partly ionic or polarized. To figure this out, we need to learn what happens to the electronic makeup of the elements as their atomic number increase. It's known that the nuclear charge increases by 1 with each element listed in the periodic table. Electrons occupy shells or energy levels with specific capacities. For instance, the first shell has room for 2 electrons, the second for 8, and the third for 18. Helium with 2 electrons in its shell and other noble gases with 8 electrons in their outermost shells are stable and show very little chemical reactivity with other elements. So the key point is, atoms tend to form molecules in such a way as to reach an octet in the outer electron shell and attain a noble gas configuration. Now, let's take a closer look at ionic bonding. Sodium, a really reactive metal, interacts violently with chlorine gas to produce a stable substance called sodium chloride. This occurs because both reaction partners attain noble gas character, transferring outer shell or valence electrons. Now, let's check the process to see why the interaction is energetically favorable. Firstly, some energy is consumed to remove an electron from sodium, which is referred as ionization potential in chemistry. The IP for sodium is 119 kilocalories per mole. However, energy is released when electron attaches another atom, which we call it electron affinity. For chlorine, it's minus 83 calories per mole. So it's calculated that our energy input must 36 calories per mole. If it's true, why is sodium chloride readily formed? That's because the electrostatic attraction between sodium and chlorine releases 120 kilocalories per mole itself. So the calculations here indicate that this reaction is highly favorable. Let's practice the last topic and wrap this up. Electron dots model is a convenient way of showing valence electrons. Here, dots show the number of electrons in the outer shell. As an example, the reaction of magnesium and chlorine is illustrated using electron dots model here. That's it for today's video. Hope it helps you a lot. Hit the like button if you found it useful, and don't forget to subscribe ChemXplain for more chemistry content.